In this video I'm going to talk about inscribed angles. So let's say that we have a circle and we have an angle like this. So the vertex is on the circle and it intersects the circle in 2 points, and we say that it subtends this arc of the circle. So this angle is called an inscribed angle. So what we are going to prove is that this angle is always twice smaller than the central angle subtending the same arc. So if you have a center of the circle, then this angle is always twice greater than this angle. Okay, so let's state it as a theorem. So any inscribed angle is twice smaller than the central angle subtending the same arc of the circle. So the central angle, it means that it's simply from the center of the circle. So basically so that's the theorem. So let's prove it. So let's draw again the picture. So we have a circle, we have an angle, inscribed angle subtending an arc, and we have a central angle. So this denoted by O, this let's denote by A, this B and C. So we are going to consider several cases when the center of the circle lies inside the angle, outside the angle, and on one of the sides. So in this case that is drawn now, like it lies outside of the angle. So let's consider maybe it would be more convenient to consider first the case when it's inside, because it would be easier. It's easier even to start with the case when it's on the side. So let's say that this is point A, and we are considering this angle. So the center of the circle lies on the side, on one of the sides of the angle, on the segment AC. So in this case, we notice that OA, so this segment is equal to this segment because these are radii of the circle. So OA is equal to OB. Okay, because this is O is the center of the circle, so these are radii of the circle. So then this triangle it has like two sides equal, therefore the corresponding angles must also be equal. So so from this it follows that the angle, so basically this angle is equal to this angle. BAO is equal to angle ABO. Okay. So, but now now we have the angle, the central angle. The central angle that we need is BOC. We notice that this is an external angle to this triangle, right? And we know that the external angle is equal to the sum of the two other angles of this triangle. So it would be equal to BAO plus ABO, and these two are the same. These two are the same as here, so therefore this is equal to twice the angle BAO, or we can write BAO is the same as BAC. It's simply the same thing here. So this would be twice angle BAC. So this is what we need to prove. So BOC, this is the central angle, is equal to twice the inscribed angle. So basically this concludes the proof of the case. So this was case 1. Case 1 when O belongs to AC. And we proved this case. So when the center of the circle lies on one of the sides of the angle. So basically case 2, let's consider when the center of the circle is inside the angle BAC. So this would be like this. Okay, here is the center, and let's draw it like this. So now we have the inscribed angle and the central angle subtending the same arc. So now what we do is basically we draw a line through through A. So let's recall the letters that we use. So here is B, C, O. So we draw the line AO up to the intersection with the circle, right? So, and now we notice that our inscribed angle is like it can be represented as the sum of these two angles, right? So, and both of them are inscribed for this point. So let's denote this point D. So now we have two arcs, BD and DC, and we have two inscribed angles and two central angles, and we basically we can use now the already proved case 1 of the same statement. So we notice that so now we have this inscribed angle and this and this central angle. So the angle okay, so we write that the angle BAC, the whole inscribed angle that we need, like it is or rather, let's start with the central angle. Yeah. So the angle, the whole central angle, BOC, is equal to the angle BOD plus the angle DOC, right? So this angle is sum of this and this, right? This and this. So now we apply the already proved case 1 for this central angle. So BOD is equal to twice the angle BAD, and now DOC is equal to twice the angle. So DOC is equal to twice the angle DAC. So in total we have twice the sum of angles BAD plus the angle DAC, and this is equal simply to so BAD. So again BAD plus DAC. So this is simply the whole inscribed angle. So twice the angle BAC, and this is what we need. So we look at the beginning and at the end. So BOC is equal to twice the angle BAC. So this is what we needed to prove. So the case 2 is also proved, and similarly the case 3, which says that that the center O is outside of the angle BAC. So this is the picture that I drew at the beginning. So the center is here, A, B, C, like this. So this is actually similarly. We can consider it similar. So we consider the line AO, and we continue it until the intersection with the circle, right? So this we call D. So in this case, the angle that we need so let's start with the central angle. So it's BOC, the central angle that we need, is equal to the difference between BOD. Instead of the sum, as was in case 2, here it would be the difference. So it would be BOD minus the angle, so BOD minus COD. And this is equal to, so BOD is equal to, by the case 1, it's equal to twice the angle BAD, right? BAD, because this is the BAD is the inscribed angle subtending the arc BD, and BOD is the central angle. So, and the second one, COD, is the central angle subtending the arc CD, and we have the inscribed angle CAD subtending the same arc. So minus twice the angle CAD, right? Now we can rewrite it as twice the difference of these angles, BAD minus CAD, and this is equal to so BAD minus CAD, so this one minus this one. This one minus this one. So it would be twice the angle BAC, and this is what we needed. Look at the end and at the beginning. We conclude that BOC is equal to twice the angle BAC. So this concludes the proof of the third case and of the whole theorem, because the 3 cases exhaust all possible cases. So now let's consider a corollary of this theorem. Corollary that all inscribed angles subtending the same arc are equal between each other. Angles subtending the same arc are equal between each other. Yeah, so basically we have have a circle, we have some arc, and we have a bunch of inscribed angles that subtend the same arc. So this, let's draw it in blue. So all of these inscribed angles, they are equal to each other because each of them is equal to half of the central angle. Half of the central angle subtending the same arc. Therefore, they are equal to each other. So the proof is simply to notice that all of this, so all of these inscribed angles are equal to 1/2 of the same central angle subtending this arc of the circle. So like if we have central of the circle here, then this would be the central angle, and each of these inscribed angles is equal to half of the central angle, and the central angle is only one. Like we have only one central angle that subtends this arc. So it's the same central angle for all inscribed angles. So therefore they are equal between each other. So therefore they meaning the inscribed angles are equal they are equal between each other. So this concludes the corollary. So that's it for this video.